Covalent bonding. We discussed ionic bonding in the previous chapter. We're supposed to discuss covalent bonding in this chapter. Covalent bonding is actually a pair of electrons shared between two atoms. Now, what is going to hold that? Because in ionic bonding, we were discussing strong electrostatic forces of positively charged particles with negatively charged particles. Covalent bonding is somewhat different. A shared pair of electron is right in between two nuclei, and nucleus of A is attracted to the electron pair. Nucleus of B is also attracted to the electron pair. Shared pair of electrons, one from each atom. So the number of attractive forces are actually still higher than the number of repulsive forces, which keeps both the atoms intact, and hence the covalent bond. So let's discuss a few examples in order to make it easy. Covalent bonding in a hydrogen molecule. Covalent bonding is also shown with the help of dot and cross diagrams, but this time we're not going to lose electron from one atom and gain in the other. Instead, we're going to share electrons. And what we are going to do is draw circles sharing those electrons, which are going to overlap one another in order to show the share. Hydrogen atoms form diatomic molecules with the formula of H2, means a molecule has two hydrogen atoms and each sharing one electron. The atoms of hydrogen molecules are joined together by a covalent bond. The covalent bond between hydrogen atoms is very strong because of the nucleus able to attract the shared pair of electrons. Now, molecules contain certain fixed number of atoms which are joined together by covalent bonds. Hydrogen molecules are said to be diatomic because they consist of two atoms. Other sorts of molecules have as many as thousands of atoms joined together, for example, proteins or DNA. Remember that although the electrons are drawn as dots or as crosses, there is absolutely no difference between them in reality. The dots and crosses are simply the illustration that tells us where the electrons come from in two different atoms. The significance of noble gas structures in covalent bonding. In H2, each hydrogen atom has only one electron to share, so it can only form one covalent bond. The shared pair of electrons is in the outer shell of both. Therefore, each atom has the same number of electrons as a noble gas, nearest noble gas, helium in this case. Now, let me explain that a helium atom has actually two electrons in its outermost shell. One over here, and it has noble gas configuration for the first shell. So hydrogen atoms, if you take a look at them, they will have two electrons after they have made the sharing. Both electrons will actually revolve on both the atoms. They will go over here. So this atom would consider having two electrons, and then they will go like this. This atom would also consider having two electrons. So both hydrogen atoms would seem like they have the nearest noble gas configuration, in this specific case, helium. Let's clear it up, move forward. So virtually all of the molecules you'll meet at this level, electrons would be shared. So hydrogen atoms have a total of 2 electrons in their outermost shell, as this is the first shell. All other atoms will have 8 electrons in the outermost shell. Some people talk about the octet rule, referring to this 8. Octa means 8. Octet rules means to have 8 electrons in their outermost shell to have the nearest noble gas configuration or the stability. We're talking about neon first 20 atoms, as we discussed in the previous chapter. Now, if atoms have 8 electrons in the outermost shell, they have the same number of electrons as a noble gas atom. They're isoelectron with noble gas atom. Remember, neon. Now, if there is one atom in the middle and other atoms are joined to it as CH4 or PCl3, the outer atoms will virtually always have 8 electrons in their outermost shell, or 2 if they're hydrogen, because in that case, we're not talking about octet rule. Actually, in case of hydrogen or in case of helium, what we talk about is duplet rule. The rule for 8 electrons in the outermost shell is octet rule. The rule for 2 electrons in an outermost shell, which only goes for the elements of the first period of the periodic table, is duplet rule. So 2 if they're hydrogen. In fact, it's very difficult to think of an example where the outer atoms do not have 8 electrons. There are some molecules where central atom does not have 8 electrons in their outer shell, and we'll discuss those examples a little later in the chapter. Moving on, why does hydrogen form molecules? Whenever a bond is formed, of whatever kind, energy is released, and that makes the thing involved more stable than they were before. The more bonds an atom can form, the more energy is released, and the more stable the system becomes. So H2 molecule is much more stable than the hydrogen atom or two separate hydrogen atoms. So remember, the need for bonding is basically the stability. And by bonding, atoms become stable in the form of either molecules, or if there are any compounds, in the form of formula units, or whatever the kind of bonding is. Now, remember, in chemistry, we talk about things being more stable or less stable. When we do this, we're usually talking about how much energy something has. Generally, the lower the energy something has, the more stable it is. Chemical reactions usually occur so that something becomes more stable. Think about holding a book. If you let go of the book, it will fall to the floor, where it has less potential energy. Therefore, it becomes more stable. When bonds form, energy is given out, and so the substance formed had less energy, and we call it more stable. So all of the bonding, be it ionic bonding, covalent bonding, or any other kind of bonding, it's all about becoming more stable. And whenever we talk about atoms having the electronic configuration of the nearest noble gas, that's once again about stability as well. So covalent bonding in a hydrogen chloride molecule. This time we're not going to consider a molecule that has same kind of atoms. This time a molecule which has different kind of atoms. It's made up of one hydrogen and one chlorine atom. The chlorine atom has 7 electrons in its outermost shell. By sharing 1 electron with hydrogen atom, both atoms will have same number of electrons as the nearest noble gas. Now, what that means for hydrogen is it's going to have the configuration of helium, and what that means for chlorine is the configuration of argon. Now, helium has the configuration of 2, which hydrogen has achieved by sharing the electrons. And this time, chlorine has the configuration of argon, which is actually 2, 8, 8. And again, it becomes stable this way. So what happens after sharing the electrons? They have the configuration of the nearest noble gas. They become stable by sharing the electrons, and outermost shells get complete with respect to octet or duplet rule in other elements, all other elements, and in hydrogen, respectively. Now, in figure 8.4, you'd notice the electrons in the outer shell of the chlorine are used in bonding. In the examples you will meet at IGCSE, inner electrons never get used. So the fact that inner electrons are often left out of the bonding diagrams, so that's easy. That makes the whole drawing thing easy. But be careful in an exam, only leave out the inner electrons if the question tells you to. Another way of representing the covalent bonding in HCl is shown in figure 8.5. Let's move on to figure 8.5. So that's it. You just show the outer shell electrons, and that's about it. Now, this specifically states showing outer shell electrons only. So once again, be vigilant when you're reading the question and make sure that you go with the diagram that examiner has asked you to draw. Now, we can also use lines to represent covalent bonds between atoms, but be careful, the diagram shown in figure 8.6 is not a dot and cross diagram. So this is more of a structural diagram. Now, whenever he's going to talk about the structure, this is the structural diagram, and these are dot and cross diagrams, 8.4 and 8.5, respectively, showing all electrons and outer shell electrons only. So there are many ways to represent the covalent bonds, and make sure you represent them the way the examiner has asked you to. Moving on. Covalent bonding in a chlorine molecule is pretty simple. Again, it's a single bond, one bond only, where there is sharing of 1 electron from each of the chlorine atoms. Both the chlorine atoms will then have 8 electrons in their outermost shell after sharing this one. So this is the entire structure. This is the structure with just the outer shells. And whenever you need to draw it with the help of a structure, it can simply be this, and the chemical formula becomes this. So that's how we go with it. Let's discuss some other structures, a little bit bigger structures. Covalent bonding in methane, ammonia, and water. Now, methane, ammonia, and water all consist of hydrogen, but apart from hydrogen, methane will have carbon, ammonia will have nitrogen, and water is going to have oxygen. So their electronic configurations are shown first. Let's move on. So first of all, methane. Carbon has 4 electrons in its outermost shell. In order to go for the octet rule, it requires 4 more electrons. So it shares it with 4 separate hydrogen atoms, as you can see over here, and a single bond with each of them would get the trick done. And hence, this is the structure of methane. It can be drawn like this in case of structure. The diagrams given in 8.9 are dot and cross models for the entire structure or just with the outer electrons on. Methane has the formula CH4. Moving to ammonia, nitrogen has 5 electrons in its outermost shell. Therefore, it requires to share 3, hence 3 separate single covalent bonds with each of the hydrogen atoms. And thus this kind of structure, we can separately draw it like this. In case of ammonia, you'll be amazed to see that apart from this structure, there is a pair of electron that is present as a part of outermost shell, but does not participate in bonding, which is drawn right over here on the top of ammonia. We are going to later call this pair as lone pair. This is to differentiate this pair from these 3 pairs, which are all actually known as shared pairs. You may also call them bonded pairs. This is a way to differentiate the electrons. So if that's present as a part of outermost shell and participate in bonding, they are known as shared pairs or bonded pairs. If the electrons are present as a part of outermost shell and do not participate in bonding, they are known as lone pairs. Moving on to the structure of water. Oxygen has 6 electrons in its outermost shell. So what happens is that it's going to only share 2 and complete its octet, 8 electrons in its outermost shell, 1 with each hydrogen atom. So the formula becomes H2O, and you would see that it has 2 lone pairs and it has 2 bonded pairs or shared pairs, right? So shapes of molecules, methane and water has been drawn differently than what we can see over here. A methane molecule is tetrahedral. A water molecule is bent. So by understanding the bonding in a covalent molecule, it is possible to work out the shape of the molecule. Pairs of electrons in the outer shell of the central atom repel each other and will therefore tend to get as far apart as possible. For example, in a methane molecule, there are 4 pairs of electrons around the central C atom. And for these to be as far away from each other as possible, they must be arranged in a tetrahedral shape. A tetrahedron is a triangular pyramid. So they are far apart from one another in this case. There are also 4 pairs of electrons around the central atom in water. 2 of these pair of electrons involved in covalent bonds, and 2 are pairs of electrons in the outer shell of oxygen, which are not involved in bonding. Let me draw it again for you. 2 of the pairs are purely of oxygen, and 2 of them are shared pairs, which are in a covalent bonding with the hydrogens atoms. These are often called lone pairs or just lone pairs of electrons. The 4 pairs of electrons are also arranged in a tetrahedral arrangement. So the actual shape of water molecule is described as bent or V-shaped. The fact that water molecule is bent and electrons are attracted to different extent by oxygen and hydrogen atoms means that a water molecule is polar, has a slightly negative and a slightly positive end, and that a stream of water can be bent by electrically charged object, as you can see in this diagram. So they are going to have a little bit of charge, not complete charges in them, a little bit of charge, and we are going to use the word polar for that purpose. Moving on. Covalent bonding in a slightly more complicated molecule, ethane. Ethane has the formula C2H6, 2 carbon atoms, 6 hydrogen atoms. Now, there is a carbon-carbon covalent bond involved. However, there are a lot of carbon-hydrogen covalent bonds involved in there. Take a look, there is only one carbon-carbon covalent bond. However, there are 1, 2, 3, 4, 5, and 6 carbon-hydrogen bonds. This is an organic compound. We're going to study it in Unit 4, Organic Chemistry, and it's mainly made up of carbon as the central element. When drawing molecules containing carbon and hydrogen, it is useful to remember carbon always forms 4 bonds by sharing 4 electrons, and hydrogen always forms 1 bond by sharing 1 electron. Not just that, if you are going to go with this hint, you better also note that nitrogen is going to form 3 bonds, carbon is going to form 4, oxygen is going to form 2, and hydrogen and all of the halogens, I'm going to represent hydrogen with H, but all the halogens with X are going to form 1 bond each. So if you know the number of bonds, it is going to be easier for you to work them out in dot and cross diagrams. Let's move on. Multiple covalent bonding. Now, covalent bond is not just about sharing 1 pair of electrons. It can share more. An oxygen atom has 6 electrons in its outer shell. So if 2 oxygen atoms combine, they will both share 2 electrons each. This means that each atom will have 8 electrons in their outermost shell. Therefore, 2 shared pair of electrons between the oxygen atoms represent a double covalent bond, or we simply call it a double bond. A double bond is actually 4 electrons shared between 2 atoms and is shown by a double line like this. This is for oxygen molecule. So multiple bonding includes double bonds and triple covalent bonds. Next example is of a triple covalent bond between nitrogen atoms. A nitrogen has 5 electrons in its outermost shell. And if 2 nitrogens are supposed to combine, they will both share 3 electrons each. And that would become a sharing of 6 electrons between 2 atoms, which is a triple covalent bond and shown by 3 lines. Each atom shares 3 electrons. It's known as a triple bond. Nitrogen gas consists of nitrogen molecules bonding like this. The triple bond from the sharing of 3 pairs of electrons between 2 nitrogen atoms is very strong, needs a lot of energy to break. That's why nitrogen is relatively unreactive. And that's going to go true for all the triple bonds. They're going to be strong, and in order to break them up will require a lot of energy. Now, double bonding can also be explained for carbon dioxide. Carbon has 4 electrons in its outermost shell. Oxygen has 2. And oxygen only needs to make 2 bonds in order to have its octet complete, while carbon does 4. So you would see that carbon is making 2 double bonds, 1 on each side with each of the oxygen atoms, while oxygen is only making 1 double bond per atom. So that stabilizes oxygen for its octet as well as carbon for its one. So that's this kind of structure for carbon dioxide. Moving on, the double bond in ethene. Ethene is rather like ethane, except that it has 2 hydrogen atoms attached to each carbon atom because there is a carbon-carbon double bond instead of carbon-carbon single bond, unlike ethane. So there is a double bond in between, and carbon are sharing 4 electrons in total between 2 atoms, 2 electrons per atom. And there are the hydrogen atoms that are attached to it with single bonds. With organic compounds such as ethane and ethene, you'll have to look at their names very carefully. Even one different letter in their name can matter. Ethane and ethene are completely different compounds. So a mistake of vowel, and there you go, everything seems incorrect. Moving on. Organic molecule contains halogen atoms. Bromomethane has the formula of CH3Br, 3 hydrogen atoms and 1 bromine atoms joined at the central carbon atom. Bromine has 35 electrons, and we have not learned how to work out the electronic configuration of atom with 35 electrons. But if we know from the periodic table, and bromine is present in group 7, it has 7 electrons in its outermost shell. So it's pretty much going to behave like chlorine or fluorine in this case. It will only share 1 electron, form a single covalent bond, and will satisfy its octet. So if you take a look at it, this would be the structure of bromomethane, which is CH3Br. Probably more complicated, the most complicated molecule for which you could be asked to draw a diagram would be something like chloroethene. When drawing chloroethene, remember that carbon will form 4 covalent bonds. Hydrogen will form 1, fluorine with 1. That is something I've explained earlier. So I think it's going to be pretty easy. There are 4 electrons in between carbons to form their double bond. So every hydrogen is going to connect with a single bond on 2 single bonds per carbon atom actually. So hydrogens, 2 of them with 1 carbon, and 1 hydrogen and chlorine with 1 carbon satisfies, and there you go, you have the structure for chloroethene. So dot and cross diagrams are somewhat easy if you're only working with the outermost shells. The structure of chloroethene probably is the most difficult one. However, any kind of structure can be worked out if you know how to balance the octets or duplets for specific elements, and you know how many bonds it's going to form to get stabilized by completing the octet or duplet. So if you remember, carbon 4 bonds, nitrogen 3 bonds, oxygen 2 bonds, hydrogen and halogens 1 bond each, it would be easier for you to form any kind of structure in the similar way. Moving on, some more difficult molecules where the central atom does not have 8 electrons in its outer shell. It may have less, may have more. So let's discuss both types of examples. BF3, boron trifluoride, is an example of having less electrons in the outermost shell. Boron is the central atom. Fluorines are the outer atoms. Each fluorine will share 1 electron each to complete its octet, as it has 7 electrons in their outermost shell. Boron, however, has 3 electrons in its outermost shell. It tries to share all 3 and still not able to complete its octet. So boron actually, in this case, you will find that boron has only a total of 6 electrons even after sharing. So this is the kind of example in which central atom does not have complete octet. Let's move on to the kind of example where central atom has more electrons, what they're supposed to be an octet, or more than 8 electrons, simply speaking. Sulfur dioxide or sulfur 4 oxide. The central atom is sulfur, the outer atoms are oxygen. There are 2 oxygen. Oxygen has 6 electrons in their outermost shell. They're going to share 2 each. To make a double covalent bond, that's what they do with sulfur. So sulfur is capable of forming a double covalent bond with oxygen over here and with oxygen over here. If it was just these 2 double covalent bonds, this would have worked like carbon dioxide, and the structure would be stable with having the central atom also in complete octet. But unfortunately, in the case of sulfur, it's not in group 4, it's in group 6. So there are still 2 extra electrons left out even after these double bonds. So sulfur actually has 10 electrons in its outermost shell, which is more than 8, which surpasses the octet rule. In upcoming books in A levels, we are going to have specific terminologies for these kind of atoms, for these kind of structures. The one which has less than the octet less than 8 electrons, or ones which have more than the octet or more than 8 electrons, we're going to work them with specific names. Atoms in period 3 and below, 4, 5, 6, 7, can have more than 8 electrons in their outermost shell. Maximum number of electrons that the central atom in a molecule can share is equal to the number of electrons in its outer shell. So sulfur can form up to 6 bonds and chlorine 7 bonds. Sulfur 6 bonds, the example is SF6, and chlorine 7 bonds, our example is HClO4, which actually are pretty much good examples of having more than 8 electrons, far more than 8 electrons, not just 10, even more than that. Now, let's come to simpler molecular structures. Molecules contain fixed number of atoms joined by strong covalent bonds. If we look closely at liquid water, there are individual water molecules where hydrogen and oxygen atoms are joined together with strong covalent bonds, but there must be also some forces between water molecules which keep them in the liquid state. These forces are known as intermolecular forces, which exist in between the molecule. So yeah, there are strong covalent bonds which join hydrogen and oxygen atoms, but the intermolecular attractions between the water molecules are much weaker, and they connect the water molecules. Intermolecular literally means between molecules. Now, intermolecular forces between molecules are much weaker than covalent bonds. When we boil water, it is only these weak intermolecular forces of attraction that are broken. Covalent bonds are not broken. So whenever we convert liquid water into gaseous water, we break these intermolecular forces to allow the gas vapors escape the liquid surface. The bonds, covalent bonds between hydrogen and oxygen are not changed. When a substance consists of molecules with intermolecular forces of attraction between them, we say it has simple molecular structure. Examples of things that have simple molecular structures: water, carbon dioxide, methane, ammonia, ethane. These are all examples for those kind of structures. We have drawn their dot and cross structures above. Virtually all compounds you will encounter, covalent bonding will have simple molecular structures. Substances with simple molecular structures tend to be gases or liquids, sometimes really solids with low melting points and boiling points. The reason for this is that not much energy is required to break the weak intermolecular forces of attractions. If we compare them with ionic substances, those were having a lot of strong electrostatic forces of attraction, so they were always solids. Here, in case of covalent bonds, just the weak intermolecular forces, hence mostly liquids or gases. Melting and boiling points increase as relative molecular mass increases. The halogens in group 7 all have simple molecular structure consisting of diatomic molecules with intermolecular forces between them. Let's take a look. Starting from top, fluorine, going all the way to bottom, chlorine, bromine, and iodine with formulas F2Cl2, Br2, and I2 respectively. Take a look that their relative molecular mass increases as we go down the series. So does the melting point and the boiling point. So much so that the state of matter will also get affected. If we know the melting and boiling points, we can always work it out. This one is a gas at room temperature. This one also is a gas at room temperature. This one is a liquid at room temperature. And finally, iodine is solid at room temperature. So the intermolecular forces actually change, and so does the melting and boiling point, which increase as relative molecular mass increases. If you continue with chemistry, you will learn that there are different types of intermolecular forces. You will come across the terms like van der Waals forces, London dispersion forces, hydrogen bonds. There is a special type of intermolecular forces between water molecules. We call them hydrogen bonds. Hydrogen bonding gives water some of its very special properties. For example, the solid ice is less than the liquid form, hence floats on the top of the liquid form. So moving on. Remember, as we melt or boil these substances, we're only breaking their intermolecular forces of attraction. The boiling points increase down the group, which means we have to put in more energy to break the intermolecular forces. As the relative molecular masses increase, the intermolecular force of attraction must become very stronger. That's why the melting and boiling points are increasing. This is something we see quite often in chemistry. For example, boiling point increase along the series CH4, C2H6, C3H8. We're going to study that in organic chapters. And as the relative molecular mass increases, this increases too. Now, it is not always the case that melting point and boiling point increase as the MR increases, and really the rule only applies to sets of very similar substances such as halogens or alkanes, like the ones we discussed over here. Some examples where these rules don't work are water, ethane, ammonia, and phosphine BH3. And you would see that they are very different. And instead of a boiling point increase, there is a random decrease. So this only goes with similar substances, does not go with the entire periodic table or stuff like that. Some other physical properties of covalent compounds. Covalent molecular compounds do not conduct electricity. Molecules don't have any electric charges on them. They're not ions. All electrons are held tightly in their shared pairs. They're not able to move from molecule to molecule. So they are insulators and do not conduct electricity. Covalent molecular substances tend to be insoluble in water. Some exceptions to this are ethanol and substances such as ammonia and HCl that react with water as they dissolve. Covalent molecular substances are often soluble in organic solvents, and we've discussed that organic solvents can be ethanol or others such as petrol, carbon tetrachloride, so on and so forth. Giant covalent structures. Diamond is a form of pure carbon. Each carbon atom in diamond has 4 electrons in its outermost shell and can form 4 covalent bonds. But in diamond, each carbon bonds strongly to 4 other carbon atoms in a tetrahedral arrangement. Now, in methane, we were actually connecting this carbon atom in the center with all hydrogen atoms. But this one's different. Carbon is connected to other carbon atoms, which are further connected to other carbon atoms, and the entire structure goes in a loop in its entirety. Carbon atoms keeps on continuing with their 4 covalent bonds in all 3 dimensions. Hence, we call the structure as a giant covalent structure. It is not a molecule because number of atoms joined up in real diamond is completely variable and depends upon the size of crystal. Molecules always contain fixed number of atoms joined by covalent bonds. Diamond, in turn, because of this structure, is going to have a high melting and boiling point because very strong carbon-carbon covalent bonds which extend throughout the structure in the whole crystal in all 3 dimensions. So a lot of energy has to be supplied in order to break these strong covalent bonds. So this diamond really has very high melting and boiling points. It's important to realize this is different from the simple molecular structure we saw above, such as CH4 or methane. We only had to supply a little bit of energy to melt it or to boil it. Before we move on further, a tetrahedron is a triangular-based pyramid. In a tetrahedral arrangement, one atom is at the center of the tetrahedron, and the atoms it is attached to are at the 4 corners. Look carefully. The 5 top atoms in the figure is 8.26. If we look at it, just a second, this one is the central carbon atom. It is connected to 1, 2, 3, and 4 carbon atoms, all equally distant to one another, making sure that the electrons that repel each other are equally distant from one another, and hence the tetrahedral arrangement. Again, figure 8.26, some carbon atoms seem to be forming only 2 bonds or even 1 bond. That's really not the case. We're showing a very small part of it. The whole structure has every carbon making 4 bonds each, all single covalent bonds to 4 other carbon atoms, and the structure in its entirety goes on with the same number of bonds. So let's move on. Now we need a lot of energy to break the weak intermolecular forces of attraction. In diamond, there are no intermolecular forces. It has a giant structure. There are no molecules. So covalent bonds are very strong and must be broken in order to melt or boil it. Hence the high melting and boiling points. In general, all substances with giant covalent structures are solid with high melting and boiling points because of the large energy required. Other substances with giant covalent structures include graphite and silicon dioxide, SiO2, which are discussed below. Diamond is very hard. Again, a lot of energy has to be supplied to break the bonds. Drill bits can be tipped with diamond for drills used in stone and rock. Diamond can drill into anything because of being the hardest natural substance. Diamond does not conduct electricity because all the electrons of outer shells of carbon atoms are tightly held in covalent bonds and they cannot move around. As there are no ions and electrons to freely move, the current cannot be carried, hence diamond does not conduct electricity. Diamond doesn't even dissolve in water or any other solvent. This is again because of the huge lattice, a lattice that is made up of strong covalent bonds. Diamond conducts heat very well, better than any other element. As one end of the crystal is heated, the atoms vibrate more and more, and the vibrations move on to other atoms. The strong bonds throughout the giant structure mean these vibrations are quickly transmitted from one end of the crystal to the other. Hence, diamond is a very good thermal conductor, but diamond is a very uh, good electrical insulator. Graphite. Graphite is also a form of carbon, but the atoms are arranged differently. It also has a line structure, but it has a layered structure. Rather than like a pack of playing cards, the layers are on top of one another. In a pack of cards, each card is strong, but the individual cards are easily separated. The same is true in the case of graphite, which we usually use in pencils. Now, atoms in a layer of graphite are hexagonally arranged, so you can see 6 carbons on the 6 corners of the hexagon, and the hexagons are connected together. But if you have an edge-on view of the layers are connected in between with weak forces of attraction between the layers. The gaps between the layers are much bigger than the distances between the atoms in the layers. So this is the structure of graphite. Because of this specific structure, the hexagons, the layers, the weak forces between the layers, but having a larger gap, this brings the graphite its specific properties. Let's discuss a few of those. Graphite is a soft material. Although the forces holding the atoms together are very strong in each layer, but the attraction between the layers are much weaker and not much energy is required. We can easily push the layers and they slide over one another, can easily be flaked off. And the same thing goes around with the pencil and it leaves a trail. We call it handwriting. Graphite mixed with clay to make it harder to be used in pencils. When you write with a pencil, you are leaving a trail of graphite behind on the paper. Poor graphite is so slippery that it can be used as a dry lubricant. For example, powdered graphite is used to lubricate locks. Now, graphite has high melting and boiling points. To melt foiled graphite, you don't have to separate the layers. You have to break up the whole structure, including the covalent bonds, which actually needs a lot of energy because the covalent bonds are very strong. Actually, the reason that the layers slide over one another fairly easily is more complicated than this, and graphite is not a lubricant in a vacuum. Graphite being a lubricant relies on water molecules sticking to the surface, and this does not happen in a vacuum. Now, graphite conducts electricity. If you look back at the figure, the edge-on view, each carbon atom is joined to only 3 others, and each carbon atom uses only 3 of its outermost shell electrons to form 3 single covalent bonds. The 4 electrons in the outer shell of each atom is free to move throughout the layer. So the electrons that are free to move are known as delocalized electrons, and the movement of these delocalized electrons allow graphite to conduct electricity in between the layers. Graphite is also insoluble in all solvents because it would take too much energy to break all the strong covalent bonds. Graphite has less dense than diamond because the layers in the graphite are relatively far apart and the distance between the layers is more than twice the distance between the atoms in each layer. In sense, graphite crystal contains a lot of wasted space, which there isn't any in a diamond crystal. That's why diamond is dense and graphite is less dense as compared to it. C60 fullerenes. Diamond and graphites are 2 allotropes of carbon. Allotropes are actually different forms of the same element because of having differently arranged arrangement of atom. For example, diamonds are tetrahedrally arranged carbon atoms, and graphites are hexagonally layered arranged carbon atoms. Another allotrope is carbon 60 fullerene. Diamond and graphite have both giant structures, but C60 fullerene has a simple molecular structure only consisting of 60 carbon atoms. In solid or liquid C60 fullerene, there are carbon-60 molecules with weak intermolecular forces between them. The fact that C60 has a simple molecular structure has a big influence on its physical properties. Let's go through a few of those. Fullerene has lower melting and boiling points than both diamond and graphite because of having a smaller structure. When fullerene is melted, only the relative weak intermolecular forces of attraction must be broken, these bonds, right? So it does not require as much energy as much we required for diamond and graphite. Now, moving on. There are different fullerenes where the molecule contains different number of carbon atoms. That's why we include the C60 in the name, because it can be say 60, say 50, C72, C70. There are many different types. However, C60 is the only one we discuss in your course. C60 fullerene is not as hard as diamond. It does not take as much energy to break the intermolecular forces, so as compared to diamond. So it's not that hard. C60 fullerene does not conduct electricity. All carbon atoms in C60 only form 3 bonds. The fourth electron, each atom can only move around within each C60 molecule. Electrons cannot jump from molecule to molecule, so they don't conduct electricity. Unlike diamond and graphite, C60 fullerene does dissolve in some solvents. Only weak relative intermolecular forces are supposed to be broken, which are really easy to break. That's why C60 fullerene can dissolve in a few solvents. That finishes this chapter. Thank you.